To cap off our discussion of spectral efficiency, I'd like to introduce a concept to you known as the channel capacity, and it is discussed in these sections of the Scholar textbook. So this is really an introduction to the third pillar of the communication system. The three important criteria were, of course, first, the bit error rate versus EB over N0, or the power efficiency. Then the spectral efficiency, which we've defined rigorously now as being the data rate and data bit rate divided by the occupied bandwidth. And the third item is cost or complexity. We've talked about cost. We've talked about less costly receivers, which are non-coherent and do not require phase lock loop in order to recover the phase. But we haven't talked so much about just complexity. And we're going to be talking about that a great deal during the second half of the course when we talk about equalizers and we talk about error correcting codes. So in particular, error correcting codes will be very effective in greatly improving the bit error rate. So by adding more digital signal processing to do error correction, we will be able to improve the performance, power efficiency. However, that will come at the cost of great complexity, and of course complexity brings cost. But the question that we're answering today is there a limit to how much I can throw complexity at a problem? If I'm willing to pay, is there a limit to how much better I can do using this digital signal processing? And that is answered directly by this concept of the channel capacity. So the channel capacity is given by what we know as Shannon's law. It was developed by Claude Shannon sometime in the 50s, I believe. And it applies, first of all, only to an additive white Gaussian noise channel. And it says that the channel capacity for a given signal to noise ratio, which we'll call SNR, and the bandwidth, which we call W, that the capacity we define by this equation, which is W, the bandwidth, times the log base 2 of the sum of 1 plus the signal to noise ratio. This is the equation which gives the channel capacity, but I should say that the definition of the channel capacity is how is our ability to send C bits per second with the probability of error as small as we want. So if I want to get smaller and smaller and smaller probability of error, I can throw my complexity at this problem. I can spend more money, more DSP, and get a better probability of error. But when I try to send even 1 bit per second more, that will no longer be the case. And that is, this limit is called C, the channel capacity, and you can see the units are in bits per second. So if we were going to take this very simple equation for the additive white Gaussian noise channel, and I was going to plot on the x-axis signal to noise ratio, and on the y-axis this channel capacity, let's say I normalize the channel capacity to make it C divided by W, so the capacity divided by the bandwidth, then I would get a curve that looks something like this, log 2 of 1 plus the signal to noise ratio. Notice, first of all, that in the y direction we have the units, which are bits per second per hertz. And so, of course, these are the units of spectral efficiency because we're talking about the capacity, the maximum number of bits per second, divided by the bandwidth. And this curve that I've plotted is the borderline. And it is the borderline between what is attainable and what is unattainable. So in green here, these are practical systems. We would be able to create a system that had this combination of SNR and spectral efficiency. But if we tried to push it and go up into this region, this would not be possible That's what Shannon laws tells us, that we just simply can't improve it. So it doesn't matter, how strong the signal to noise ratio is. At a certain point, I'm just not going to be able to send more information. So I said that this is in units of spectral efficiency. And if we think about this curve, when it's C divided by W, the far end of the curve up here is where the spectral efficiency goes to infinity. And the bottom end of the curve here is where the spectral efficiency goes to 0. So if I have a very strong signal, then I'm heading towards being very spectrally efficient if I'm riding on this curve. And down here, and that's where I'm being very spectrally inefficient. So I'm in the very weak signal to noise ratio. And in this case, I'm making the trade-off of using my complexity, using my spectrum to try to achieve more performance. So let me flip this around and say that I want to plot W divided by C, and now it's hertz per bit per second. And, I get the same curve, but now this would be the practical system. This would be the unattainable one. This would be efficiency going to 0 and efficiency going to infinity. So this is just another way that you will sometimes see Shannon's complexity plotted, but we're going to use this version of the plot. So if we look here, there's something we have to be careful of, and that is that this W, the bandwidth, and the signal to noise ratio are actually related to one another. And in fact, when I use more bandwidth, I'm allowing more noise to come in, which means that my signal to noise ratio is actually going down. So it's difficult to see this relationship due to this sort of interdependency. So this choice of axes is perhaps not the best because of this interdependency, which we really can't see what's going on if we just look at this version of the curve. Because of that, we sometimes see an alternate form of Shannon's law. So the other form is very simple, very easy to remember. This is, however, a little bit more useful, I believe. So we're looking at this plot of C versus W, and we're assuming that we're actually transmitting data. R is the rate we're transmitting at, that we're transmitting our data at the maximum capacity. So we're evaluating it, if you will, our system as we fall on this line of the limit between the attainable and the unattainable. So we're sending our system right at the fastest bit rate. So C over W, that's equal to log 2, and we could write our signal to noise ratio as the signal power divided by the bandwidth times the power spectral density of the noise, N0. And so here we get to see the dependency of W on both sides, W, the bandwidth appearing on both sides of the equal sign. And this is something that we're trying to isolate and put all of the dependence on W together. So what we're going to do in order to achieve that goal is we're going to say, let's multiply and divide by the capacity, C. Certainly we're allowed to do that. And again, we're interested in this equation when R, we're transmitting right at the maximum speed. So this is what we're looking at. So now I'm going to replace this C by the R, since this is the region that we're evaluating it. So I have S divided by R times N0, C divided by W. And now I'm going to write my R in terms of 1 over the bit rate. And so now I have S times the bit rate, or the bit interval, R is the bit rate. It's 1 over the time of 1 bit. So T is the bit interval. So I have S times the bit interval, and then I have, of course, the C over W and the power spectral density N0. And so what I recognize is that the energy per bit is just given by this product of the signal power times the bit interval. And so now I've got something EB over N0, which is independent of the occupied bandwidth. And I have CW on this side of the equation, CW on this side of the equation, and now I'm going to solve for C over W. And this will make much clearer what the dependency is. So this transition, we'll take the raise both sides of the equation to the 2 to this exponent. We isolate EB, and we get that EB over N0 is equal to bandwidth divided by capacity times 2 to the power of capacity divided by bandwidth minus 1. So here we have a very much clearer relationship. And so before we were plotting x-axis of SNR, and now we're going to plot the x-axis instead to be EB over N0. Notice that as the ratio C to W goes to 0, we have a limit on the EB over N0. So as C over W goes to 0, we have 2 to the 0. Excuse me. I have to multiply by these two quantities to take that limit. But if I take the limit as C divided by W goes to 0, I would find that there is a value for EB over N0. And this value, this limiting value, is minus 1.6 dB. Very, very important number, because we see now that C divided by W going to infinity, going to 0, that means the spectral efficiency is going to 0. So this is the trade-off I make. Suppose that in these 3 pillars, I completely sacrifice spectral efficiency. I have the worst possible spectral efficiency. What can I get for that? What I get for that is that I can have arbitrarily good probability of error if I have good enough DSP, if my complexity is high enough, to get good communications, even if the EB over N0 is equal to negative 1.6 dB. So even if the noise is stronger than the signal, I can still get good, reliable communications. It just takes a lot of spectrum, and it takes a lot of complexity. So if we looked at this alternative plotting of W over C, the hertz per bits per second, you would see that there's actually an asymptote here, now that we're plotting it against EB and 0 net SNR. And this asymptote is indeed this value of log base, the natural log of 2, or minus 1.59 dB. And this, of course, represents the limit where the spectral efficiency goes to 0. And here, of course, in the opposite direction is when we're being like super spectrally efficient, which means that we have to have more EB over N0. And again, this curve breaks the plane into 2 areas, the attainable and the unattainable. I'd like to mention that this limit of minus 1.6 dB was actually in some curves that we've seen. And in particular, it was for MPSK. So here is the bit error rate curves for orthogonal M-array. It doesn't matter which orthogonal, but we were talking at the time about FSK. And we started at k equal 1, this curve for binary, and we said that as we made more and more points in the constellation, more and more frequencies in the case of FSK, that we could improve our performance and that our curves were getting closer and closer to the origin. But there is a limit, and this limit is located exactly at that calculation of minus 1.6 dB for EB over N0. And so you can see that even as we're increasing it substantially, we're going to hit a wall at one point. So there is a limit. So I can throw complexity at the problem. I can throw a lot of frequency occupancy, but I can't do that forever. There's a certain limit, and I cannot break. And there it is. So this is the limit, if you will, for an infinite number of frequencies in FSK. Now I want to draw your attention to these 3 points that have appeared here. Now suppose I take this curve for FSK and I ask, what are the values for the EB over N0 that's required if I wanted to achieve probability of error equal to 10 to the minus 5? So there would be one value for the EB over N0 needed if I had binary, k equal 1. And if I had quaternary, k equal 2, here it would be 10, EB over N0 equal to 10, etc. And so I could look at all of these intersections here with 10 to the minus 5 and get different values as a function of m, the number of points in the constellation. Because I'm going to take these points now and I'm going to plot them on the capacity calculation that I showed you previously. I'm also going to do that with MPSK. So let's take the MPSK curves. I set the same quality, the same 10 to the minus 5 performance, and I will see, different points for different values of the constellation. And of course I could do that for QEM as well. So this is why I'm doing it. I want to show you what we call the bandwidth efficiency plane. And in this, we're plotting EB over N0, and this is R over W. R over W because this plot is for R equals C, and this is the Shannon capacity. You notice that this curve is smooth and then seems to change here. That's only because we changed the scale. So here, the negative EB over N0 has a different scale so that we can see this Shannon limit more clearly, whereas on the positive EB over N0, we want to spread things out so we can see other information. So once again, the gray area is the area we cannot achieve because it violates the Shannon limit. And in the white region is the region of interest. These are practical systems which can be attained. So we've got some points that are plotted here, and these points that are plotted here are coming from the calculations I showed you previously. Again, EB over N0 versus R versus W. Don't forget that in this region we're getting to infinite spectral efficiency, whereas in the other region here it is 0 spectral efficiency. And now to see what these points are that are scattered around this plot, we're going to go back to this curve for MFSK. And these points, if you look here, it's the squares that are used for MFSK. So we have these values which are giving me EB over N0. So for instance, here it looks like it's about 12.5. If I look at something like 12.5, I would get this square. But I'm plotting, this is EB over N0, and what I'm plotting it against is its spectral efficiency. So I would look at log 2m over m, do the calculation, and see that the spectral efficiency for binary FSK is 1/2. And if I did the same thing for 4, so I'm taking this ordered pair. The x value I take from this intercept point with 10 to the minus 5. And the y value is my calculation of eta. What's eta for this modulation format? And you can see that all these FSK points are falling down in this region where we're sort of in the direction where we're becoming less spectrally efficient. And so we call this region the power limited region. Why? Because if we had a system that was limited in power but was willing to go towards the sacrificing spectral efficiency, this would be a good place on this bandwidth capacity curve to look for a solution. Now we could do the same exercise now with QPSK. And for QPSK, again, this is coherent PSK in this case, we would find these various points which are highlighted and given in the circles. And we can see that we're falling in a completely different region of this bandwidth efficiency plane. And I could go on and do the same thing for QAM. And of course, QAM is even more a good trade-off. And you can see the trade-off very clearly here. Because M equals 16, they both have the same spectral efficiency, both PAM and QAM. But we can see that now the required EB over N0 is smaller for QAM than it is for PAM, which is why we're seeing this green triangular points becoming closer to the capacity limit than the ones for PSK. Now these numbers, you recall that we chose them because it meant 10 to the minus 5. And then it shows here that if I were to change this to 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, of course I would be requiring more and more EB over N0, so it would be normal that these points would sort of move out in this direction. So here we have what we call the bandwidth limited region, and in this region is where we find the PSK and the QAM modulation. So we had this concept before about power limited versus band limited, and we talked about it in terms of definition and which solution would be more. But here on the bandwidth efficiency plane, we really get to see how we can take our quantitative results and plot them together so that it brings out for us which should be used. So the bandwidth limited region basically refers to everything where the efficiency is above 1 bits per second per hertz. And in the power limited region, we're looking at values where we're going less than 1 bit per second per hertz. Okay, thank you.